Hello everyone, I'm Tonglin from the University of Science and Technology of China. Today I will present our work titled A Perceptive Soft Finger for Shape and Texture Recognition. My presentation will be divided into the following four parts: motivation and background, working principle, conclusion, future work. Among the five human senses, touch plays a crucial role. Tactile perception includes pressure, vibration, temperature, thermoconductivity. Kinesthetic sensing relates to the feedback from muscles, tendons, and joints, helping us perceive things like shape, texture, and size. Humans use six common movements to detect the object, including pressure, lateral movement, static contact, wiping, lifting, and control following. Those actions help determine an object's softness, surface texture, temperature, thermal conductivity, shape, and weight. In bell-inspired sensing system, robotic grippers following similar methods to gather object information. Currently, most tactile sensing systems, whether mechanical or pneumatic, require complex setups to integrate both tactile and kinesthetic sensing. The top figure shows that robotic hand has kinesthetic perception with integrated tactile sensors at the fingertips. And the bottom figure shows that the pneumatic fingers with integrated sensors for gripping objects of different sizes. Before going into the technical details, let me briefly introduce our research. Inspired by human tactile perception, our work integrates both tactile and kinesthetic sensing. The tactile part is achieved through an inductive multimodal tactile sensors (MTS), where the kinesthetic part is realized through a self-sensing soft finger. In our work, we present a simpler method for achieving integrated tactile sensing with a self-sensing soft finger. Like a human hand, tactile perception is achieved through an MTS at the fingertip, where kinesthetic feedback comes from the self-sensing soft finger. The principle of kinesthetic is to use the mutual inductance effect of the coil. The coil is wound on the pneumatic finger, and the coil is connected with alternating current. When the pneumatic finger is bent, the coupling between the coil changes, and the inductance of the coil changes. The principle behind the MTS relies on the eddy current effect. When alternating current flows through the coil, it generates a magnetic field that induces eddy current in a nearby target. These eddy currents produce their own magnetic field, which in turn affects the coil's inductance and resistance. By modeling this system as a transformer, we derive theoretical equations that describe the relationship between the coil and the target. First, we use the console simulation to model the sensor's behavior. When pressure is applied, the coil's inductance decreases, where changes in temperature primarily affect the coil's resistance. This validates the theoretical feasibility of our approach. Next, we calibrated the sensors using PT100 temperature sensor and Futec pressure sensor, measuring the coil's inductance and the resistance in response to varying pressure and temperature. By decoupling the inductance and the resistance, we derive a matrix that allows us to compute the pressure and temperature from just those two electronic parameters. To further verify the sensor's performance, we conducted tests under various conditions, as shown in the left figures. In different temperature, the pressure measured by the MTS closely matches that of the fuel tank sensor. Similarly, about the temperature test, the temperature of the MTS values are consistent with those of the PT100 in different pressure. Moreover, as shown in the right figures, we tested the MTS with silicon blocks of different temperatures, but the same weight. The results show that the MTS can accurately detect both the temperature and the weight of an object, demonstrating its superior performance and applicability. We also applied current to MWC within the MTS, allowing it to self-heat and maintain a constant temperature. Much like a human hand, by adjusting the power, the MTS can maintain different temperature as needed. We then developed a heat transfer model for two scenarios: when the sensor is in contact with air and when it touched an object. The resulting equations show that higher thermal conductivity leads to a lower steady state temperature. Confirming the sensor's ability to recognize objects, we tested 5 objects, as shown in the table on the bottom right: cork, acrylic, nylon, glass, silicon wafer. These 5 types of objects have different thermal conductivities, so there are different steady state temperatures when the MTS comes into contact with them, as can be seen in the diagram. In the application phase, we covered an object with the white type, making its subsurface material invisible to the eye. However, the MTS was able to distinguish between material based on difference in thermal conductivity. Since humidity also affects thermal conductivities, the sensor can be used to detect moisture level in object as well. We use the 3 paper towers with different humidity as samples, and it can be seen that the sensor can distinguish them very well. For kinesthetic sensing, based on the mutual inductance principle, the further apart 2 coils are, the weaker the mutual inductance. By calibrating the pneumatic finger's bending angle with the coil's inductance, we derived a linear function between them. To evaluate this further, we tested 2 objects with different surface profiles. As pneumatic finger slid across their surface, it experienced vibrations, causing changes in coil's inductance. The phrase clearly shows that the sensor can differentiate between the 2 surface profiles. Sliding the finger across the mouse in various directions, we were able to reconstruct a rough 3-dimension model of the mouse's surface. In conclusion, we successfully integrated tactile and kinesthetic sensing in a simple system that can recognize object temperature, pressure, thermal conductivities, surface texture, and local shape. This has significant implications for future applications. Looking ahead, not only can this sensor recognize the external environment like a human hand, but it can also sense a patient's body temperature or measure their pulse. Therefore, it holds great potentials for future applications in medical devices. Thank you for listening. This concludes my presentation.